All right, no questions? Last time, I think we left off with a percent precipitation. Is that correct?
Yeah.
Okay. All right, then. This time we're going to do the next paper problem called fractional precipitation. In fractional precipitation, what you do is you take advantage of differences in solubility to separate ions. You can separate cations from other cations or separate anions from other anions. And so what we do is we separate ions based on differences in solubility. And so we'll have some kind of precipitating agent, and then we'll see, can we separate it based on precipitating agents. And so let's just take a look at some solubilities here. For KSPs. KSPs are going to be related to the solubility. They aren't exactly the same as solubility. It gets tricky because of how things split. So for example, the solubility for barium carbonate would be the square root of the KSP, whereas the solubility for barium hydroxide, because it splits up into 3 ions versus 2 ions, would be 4 times the cube root of KSP. And so it's different. Over cube root, yeah, 1 over 4. And so, what we'll do is we'll look, can we separate like cations, like for example, barium carbonate and calcium carbonate. So we might try to separate barium from calcium using carbonate as a precipitating agent. And so we'll look at the solubilities. If we look at the solubilities here, KSP is going to be related. Barium carbonate and calcium carbonate split up in the same way into 2 ions. And so the solubility will be the square root of that. So 10 to the minus 9. And then calcium carbonate is 2.8 times 10 to the minus 9. The solubilities are very similar. Do you see that? So it would be very difficult to separate barium from calcium because they both would precipitate out, basically. And so barium and carbonate might be hard to precipitate using carbonate, but could we separate it using something else, like for example, hydroxide? And so if we look at barium hydroxide is 10 to the minus 3. How about calcium hydroxide? Calcium hydroxide is 10 to the minus 6. And so there's 3 orders of magnitude difference in their KSPs, which means we might be able to separate barium from calcium by adding hydroxide. The way this would work is it would precipitate the less soluble one. The less soluble one would be calcium hydroxide because it's 10 to the minus 6, which is a lot smaller than 10 to the minus 3. We try to precipitate out the calcium hydroxide and leave the barium hydroxide in solution. And let's see how that might work in practice. So we'll just do this, trying to separate calcium from barium, or, we could pick a bunch of others. Those are cations. We can also try to separate anions as well. So in the same context, what we can do is we can try to separate out, let's say, hydroxide from some other anion. What other anion would we have potentially? Carbonate. And so could we separate hydroxide and carbonate using barium? So if we use barium, barium hydroxide is 10 to the minus 3, whereas barium carbonate is 10 to the minus 9. So in this case, what I can do is if I have a mixture of hydroxide and carbonate and I add barium to the mixture slowly, I'll precipitate out the barium carbonate first because that has a much lower solubility. And then its order is magnitude different than this one here. And so this is the strategy we look for in fractional precipitation. We look for differences in solubilities. If we're trying to separate anions, then we look, trying to separate cations and we look at an anion that might accomplish that. So let's see if we can separate barium ions from calcium ions. So let's say I had a mixture of barium ions and calcium ions in here. And, they're probably nitrates, because nitrates or acetates or chlorates are mainly soluble. And so nitrate is very popular because, and as far as metathesis goes, nitrate is not very reactive. As far as redox goes, nitrate could be potentially reactive because it's a pretty strong oxidizer. So we've got nitrates in here. So that's 1, 2, 3, 4. Actually, too many nitrates. Okay, nitrates are just going to be spectators in this particular reaction. And so what we're going to do is we're going to try to separate these using, what did we say, hydroxide? Yeah, hydroxide, because barium hydroxide is 10⁻³ whereas calcium hydroxide is 10⁻⁶. And so what we're going to do is we're just going to add hydroxide to this a little bit at a time. So we're going to start off with 0 hydroxide. There's no hydroxide in here. And then what we're going to do is we're going to just add drop by drop hydroxide. Just a little bit of hydroxide at a time. So we're going to increase the hydroxide. And eventually what's going to happen is this. It's going to be unsaturated. So let's say I don't have enough hydroxide to precipitate. Remember, what we need for precipitation is a QSP that's greater than a KSP. And so if I don't have enough hydroxide, let's say I just have a minuscule amount of hydroxide, well, then I'm going to ignore the nitrates, and we'll just look at that. And so here, I calculate the QSP for barium hydroxide. So the QSP for barium hydroxide is equal to, well, we need the QSP equation. So the QSP equation would be barium hydroxide, solid, goes to barium ions plus 2 hydroxide. Okay. And then the same thing for calcium hydroxide, solid, we get a calcium 2 plus 2 hydroxide. Now, if you look at the KSP equation, the KSP is going to equal barium ion concentration times the hydroxide ion concentration squared. And so QSP is just your barium concentration times the hydroxide concentration squared. So let's say QSP is at some number and it comes out less than KSP. If QSP is less than KSP, will it precipitate? No, it's not going to precipitate. And then we do the same thing. QSP for calcium hydroxide is going to equal some number, and it's going to be less than KSP here. So we have no precipitation. Now the two KSPs are quite a bit different because barium hydroxide's KSP is 5 times 10⁻³. Whereas calcium hydroxide's KSP is 3 orders of magnitude smaller, 5.5 times 10 to the -6. So 1,000 times smaller. So as we continue adding the hydroxide, eventually what we're going to do is we're going to saturate the solution with respect to calcium hydroxide. And so what we'll do is we're going to do a calculation here. And that is, in a fractional precipitation, we calculate the concentration of a hydroxide required to precipitate. Okay, we know that calcium hydroxide is going to precipitate first because it has much smaller. solubility. And so the concentration of hydroxide required to precipitate is equal to this. We're going to solve this equation here for hydroxide. In other words, the KSP equation. So the KSP equation for calcium hydroxide is just the same. Calcium ions hydroxide squared. So these are going to be at equilibrium. In other words, these are going to be what we call saturated. The max. And so the hydroxide concentration at the end that can be saturated is going to equal, what is it going to equal? KSP divided by the calcium concentration. So KSP divided by the calcium concentration. And then we'll take the square root of that. Here.
Those equations at the top supposed to be QSP, not KSP?
No, these are going to be KSP. And then QSP would just be what's given, the initial. So it's basically the same. QSP and the KSP equation are the same thing. Sometimes the QSP is equal to the KSP, and the concentrations just match. And so, here, we'll just write it here. QSP is, the difference between a QSP and KSP is that the barium concentration is given, whatever that concentration is, so we'll call it the initial. And the hydroxide concentration is initial. We don't know if the initial is already at equilibrium or not. Whereas the KSP equation is, it's already at equilibrium. It's maxed out. And so that's the only difference. The seventh is the same. So we use this, not QSP here, we use KSP here because we want to saturate the solution. And so in order for this, we don't have precipitation here. And so what we need here for precipitation is that the hydroxide has to be greater than this in order to start precipitation. Because if the hydroxide is equal to this, then it's just saturated and we don't get any precipitation. If it's less than this, it's unsaturated. So what we have here is we call this unsaturated. Here. Now, in order to do this, I need to know what the concentration of barium and calcium is. And so that has to be given at the beginning of the problem. What is the concentration of these? Because I assume that which one precipitates first? I assume that calcium precipitates first, but it depends on the concentration. Let's say I have 10,000 times more barium than calcium. If I had 10,000 times more barium than calcium, then barium might precipitate first because it's got a lot higher concentration. So this is kind of like Le Chatter's principle here. If I have a lot of this ion to begin with, I'm not going to need as much hydroxide to precipitate it. Whereas if I have very little calcium, I'll need a lot of hydroxide to precipitate it. And so this is why we calculate this, because this takes care of the concentration of calcium here. If it's very small, I need more hydroxide. If it's very big, I don't need as much hydroxide, so it varies. And then if these two are different, that's going to change the dynamics of the precipitation, the fractional precipitation here. To keep things easier, what we're going to do is we're going to say the barium concentration here is 0.100 molar. The problem is I have solution dilution occurring here, but we're going to ignore the solution dilution and just call 0.100 molar constant throughout. And the calcium is 0.100. We're going to make a big assumption here that the concentration does not change. And so that means adding solid hydroxide or something. So probably not solution, because if this is solution, I'm going to get solution dilution. So probably I need the solid, like sodium hydroxide. If I had solid sodium hydroxide, then what happens is the concentration doesn't really change so much. Does that make sense? Mm-hmm. Yeah. Otherwise, I'm going to have to do the X, solve for X, etc., which is I don't want to do. And so we're going to assume that the concentration assumed to be fairly constant. Okay, so let's calculate the hydroxide required for precipitation. And so the hydroxide that's going to be required for precipitation is going to be greater than because we've got to exceed KSP. And so the KSP for calcium hydroxide is 5.5 times 10 to the minus 6. And we're assuming that the concentration is the same as what we started off with, 0.100. And we'll just take the square root of that. And so what does this come out to here? 5.5 times 10 to the minus 6 divided by 0.1. And then square root of that. So 7.4162 times 10 to the minus 3. So 7.4162 times 10 to the minus 3 molar. And so to be unsaturated with respect to calcium 2+, we need the hydroxide concentration has to be less than or equal to 7. Well, if it's unsaturated, it has to be less than 7.162 times 10 to the minus 3. So we start off with very little hydroxide. Here. Let's do the same for, this is for calcium. Let's do the same for barium. So what is the hydroxide required to saturate? The hydroxide required to saturate the solution is equal to, and the hydroxide required to precipitate is going to be greater than. And so let's go. Since this splits up the same way, sometimes it doesn't. For example, the example in the book, it doesn't split up the same way. Just take a quick look at that later. So for barium hydroxide, it's 5 times 10 to the minus 3 divided by 0.100. So we'll do 5 times 10 to the minus 3 divided by 0.1. Let's square root of that one. 0.2236. 0.22361 molar. And so you can see there's a pretty big difference in the molarity here that's required. And so what we can do is we can increase the molarity of hydroxide until we hit 7.4162. When we hit 7.4162 times 10 to the minus 3 molar, then it becomes saturated in calcium, but however, it's unsaturated in barium. And so we'll increase this. Let's see, this over here. So we just continue adding the sodium hydroxide until we hit a concentration. Once the hydroxide concentration hits 7.4162 times 10 to the minus 3 molar, then it's saturated with calcium, but unsaturated with barium. And so right now then, there's enough hydroxide in there to start to precipitate out the calcium, but not enough hydroxide to start to precipitate out the barium. So we just add a little more hydroxide and then we supersaturate it with respect to calcium, which means the calcium hydroxide will begin to precipitate. Calcium hydroxide begins to precipitate. Now, based on the KSP equation, the KSP is equal to the calcium concentration times the hydroxide concentration squared. So as we increase the hydroxide, we're going to have to decrease the calcium, and therefore precipitation must occur. Okay. All right, then we're just going to continue. As we continue increasing the hydroxide, more and more calcium precipitates out. It's a common ion effect. But we can't, oops, erase the wrong one. We can't go on forever. So for example, we can increase the hydroxide up to a max. The max hydroxide that we can have is equal to 0.22361 molar. Because if we go past this, then barium will precipitate, and we'll get two precipitates. We'll get calcium and barium, and we don't want that. And so we're not going to get all the calcium out. Well, we can get it out anyway, because we'd have to add an infinite amount of hydroxide to get it out. And so how much barium remains? Well, all of it remains in solution. So we don't want the barium to come out of solution. However, hopefully a lot of the calcium came out. So the calcium becomes less and less. And we get more and more precipitate. On the bottom. I have the hydroxide here. Okay. So if we go past this, this is the max. If we go past this, then barium and calcium both precipitate. Barium and calcium both precipitate. We don't want that. And so we have to stop here. If we stop here, what we need to do is we need to calculate how much calcium remains in solution. So how much calcium remains in solution at the max hydroxide? Well, we can use the KSP equation to calculate this. So the calcium 2 ion that remains is equal to the KSP divided by the hydroxide concentration max squared. And so as the hydroxide increases, the calcium decreases. So once we hit this point here, we can go ahead and calculate how much calcium remains. And that would be 5.5 times 10 to the minus 6 divided by 0.22361 molar. So let's see what that comes out to. So at this point, we have 2.4597 times 10 to the minus 5 molar calcium ions in solution here. And we have all the barium ions left. So the calcium ions would be 2.4597 times 10 to the minus 5 molar. And the barium ions here will be 0.100 molar. We don't want any of those.
Also, for the equation for calcium remains d squared the hydroxide?
No, maybe not. I probably forgot this is for the hydroxide. Yeah, you're right, I didn't. So let me go ahead and divide it by 0.22361. 1.1 times 10 to the minus 4. Is that what you got?
Yeah.
Okay, yeah, I made a mistake there. Thanks. 1.1000 times 10 to the minus 4 molar calcium 2 plus. 1.1 times 10 to the minus 4 molar. This is, the same thing happens to me. Chapter 16 and 17, we don't have to square anything, as far as the concentrations go. We do have to square X, but in this chapter, higher orders, we don't put things again. All right, so what we need to do is we need to calculate the percent calcium that remains in solution. And so this would be the next calculation. How much? In terms of percentage, the percent calcium remaining is equal to 1.1 times 10 to the minus 4 and over the initial, which was 0.100 times 100%. So 1.1 times 10 to the minus 4 divided by 0.1 times 100. And we get 0.11% remains unprecipitated. Well, the percent precipitation, so percent calcium precipitated, is equal to 100% minus the percent remaining. (99.89%). Precipitated. So we're really only allowed 2 sig figs, but we need to carry extra digits here. So we'll go with 99.9%. Just round it. 99.9%. If it's 99.9%, is that okay? What was the complete precipitation? This is barely made it, but it's arbitrary, 99.9%. Or 99.99%. So we got 99.9% of the calcium out of there before the barium. So this is an effective way to get rid of the calcium. Although the barium is going to have a tiny bit of residual calcium in there, so it's not pure, but it's an effective separation. So we call this this would be an effective fractional precipitation. Barely. There are things that are, even more effective. For example, let's see. In the book's example, they try to separate lead and silver using iodide. And let me just look at silver. Silver iodide has a KSP of 8.5 times 10 minus 17. But if we look at lead 2 iodide, let's see lead. All right, get to the top. It's 7.1 times 10 to the minus 9. But the problem here is they split differently. Lead iodide splits up into 3. And silver iodide splits up into 2. So this problem is a little bit more complicated because we can't just look at the KSPs. The KSPs are orders of magnitude different, 10 to the minus 9 versus what was it for silver iodide? Negative 17. Yeah, this is huge. That's 8 orders of magnitude. So it should work. But the problem is that they split it differently, so you can't just look at that and see. If it works or not. So we just have to do the calculations to see. But this is the standard calculation here in this setup. Likewise, we could try to separate like bromide from chloride. In fact, separating bromide from chloride, we could try silver. So silver bromide is 10 to the minus 13. Silver chloride is 10 to the minus 10. That's cutting it close. In fact, when we do it, the calculation for chloride and bromide, it's not. We get like 80%. And it's not effective because these are just too close to one another and they split up the same way. Chloride from carbonate, maybe, no, 10 to the minus 12, but again, these split up differently. And so you can't just base it on the KSP, you have to look at the actual solubilities. Now, one of the things that we do in this particular problem is, did we calculate the solubility? No, we didn't calculate the solubility. One of the most common errors in fractional precipitation is people will calculate the solubility of calcium hydroxide and then calculate the solubility of barium hydroxide, but we don't need the solubility. What the calculation is what was the calculation? What did we calculate for a fractional precipitation?
Hydroxide is needed for each of those.
Right, that's the calculation we do. We don't calculate the solubility. We don't care about the solubility. What we care about is how much hydroxide is required for precipitation for each. And so that's the kind of calculation we're going to do here. And so the same thing with all these. And so a lot of people on the test will get mixed up because they immediately go to calculate the solubility and then they don't know what to do with it. You know, don't really know what to do with it. Okay, so fractional precipitation problem here. The next type of problem is trying to change the solubility. That is, we can decrease the solubility or we can increase the solubility by doing certain manipulations to the conditions. So, in other words, we're going to adjust the solubility, or you could say manipulate the solubility. So we can make things less soluble. So, for example, decreasing the solubility. Probably the most common way to decrease the solubility is use the common ion effect. You know, Le Chatelier's principle. And so this is what the whole principle behind precipitation. We want to decrease the solubility of certain ion to precipitate it. And so we decrease the solubility by the common ion effect. I.e., just precipitation. This is what we call precipitation. And we have precipitating agent like chloride or hydroxide or whatever. And we just keep adding it until we get max precipitation. How about increasing the solubility? What are the ways that we can increase the solubility? Increase the temperature. That's the most common way. And so increasing temperature. Most of these are endothermic, so increasing the temperature of Le Chatelier, well, it's not really Le Chatelier. Increasing temperature changes the K and makes it more soluble. You know? So increasing temperature is one way. Also, here, common ion effect, likewise, we can decrease the solubility by decreasing the temperature as well. And so there are different ways we can do this. But there are even more ways, which we'll talk about.
Agitation.
Mixing will help speed things up, but it just is a time issue. Eventually things will come to the same solubility regardless if you mix it or not. It just takes a lot longer if you don't mix it. One of the things that we try to do, and this could have an impact one way or the other, is by adjusting the pH. Sometimes if we make the pH lower or higher, that will change the solubility. And the same thing goes for this. We adjust the pH, but we don't know how it's going to impact it as well. And so it does both increase or decrease solubility. The other way is we remove biochemical reactions, and so pH and then complexing. Or other reaction to remove product. If we remove product, then Le Chatelier's will shift the equilibrium to the right. That is, it will dissolve more solid. So these are the two types of calculus. We're going to look at pH and complexing, and then other reactions that could change this. So pH for some reactions is pretty simple, like magnesium hydroxide. And so, let's do an example here. So the question would be, at what pH will 0.100 molar magnesium ions precipitate? So in this case, what we're going to do is we're going to start off at, let's say, some pH. I don't know what pH to start off with. But the magnesium ions, we'll say pH 7. This is just water. So maybe we have nitrate ions. Nitrate ions will be neutral. So we have some magnesium nitrate. And then what we're going to do is we're going to add some hydroxide to this. Hydroxide ion. Eventually, it'll precipitate now. And so in order to precipitate the magnesium, we need to have enough hydroxide to saturate it and then supersaturate it. And so this is the same calculation as we just did for fractional precipitation. We need to know how much hydroxide is required for precipitation. So hydroxide required to precipitate. The hydroxide that's required to precipitate has to exceed KSP. So this splits up just like the previous one. So the hydroxide is going to equal the square root of the KSP divided by the magnesium concentration. But this is enough to saturate it because then we'll get an equal to KSP. What we have to do is we have to supersaturate it, so it's going to be greater than this. So this is the limit here. So we need the
Professor. Right, just a comment on that effect. What does that say?
under the this
Or
one.
next, or next.
Oh, this is precipitation. PPTION.
Okay.
This abbreviation is precipitation.
This is what's I.
Oh, that is, yeah, IE and precipitation. 1.8 times 10 to the minus 11 is the KSP for magnesium hydroxide. So we'll go over here. It's going to be 1.8 times 10 to the minus 11 divided by 0.100, and we'll take the square root of that. That's going to be the hydroxide required for precipitation. It's magnesium ion. I'm sorry? Is there a square? Yeah. There is a square because this magnesium hydroxide solid is going to go to 1 magnesium ion and 2 hydroxide. And so therefore the KSP is going to equal magnesium concentration times the hydroxide ion concentration squared. And what I'm doing is I'm solving for hydroxide. When I solve this for hydroxide, I'll take the KSP divided by the magnesium, and then I want to get rid of the square by square rooting it. Yeah, so this is why it's square rooted. Yeah, just skip this step. Okay, so 1.8 times 10 to the minus 11 divided by 0.1, and then take the square root of that. This is going to give me 1.3416 times 10 to the minus 5 molar. So this is the minimum hydroxide. Actually, we need a little bit more than this to precipitate it, right? And so we need more than 1.3416 times 10 to the minus 5 molar hydroxide. which is a pOH of what? And so the pOH of this would just be the negative log of this concentration. So I'm just going to take the log of that answer. .8724. 4.8724, which means the pH is 9.1276. So this is the pH required to saturate it. Now, the pH that's required to supersaturate it, is it going to be greater than this or less than this? So we need more hydroxide. Is more hydroxide going to be higher pH or lower pH? Higher pH. So it has to be greater than this. And so in order to precipitate it, the pH must be greater than 9.1276. Now we're allowed to have 2 6/8 here, so we just say the pH has got to be greater than 9.1.
Would it be 9.1?
3, 9.13. pH has to be greater than 9.13. So this is a more straightforward problem because hydroxide is part of it. But we have ones that are a little bit more involved. The ones that are a little bit more involved are looking at removing some of the product. Like for example, how can we remove some of the product here? One way we could remove the product is we could attack the hydroxide with acid. If we attack the hydroxide with acid, then H plus and OH minus make water. And so as the hydroxide ion concentration decreases, this has got to shift right. And so this is making it less soluble, by increasing the pH makes it less soluble. But decreasing the pH, adding acid to this, although acid's not a direct participant in the equilibrium, will remove the hydroxide. And so that's what we call the combined method of KSPK. And so what we're going to look at is a little bit more complicated problem of multiple equilibria. Now, for multiple equilibria, we have the stepwise method and we have the simultaneous method. Okay, this is another method, but we can only use this when we meet certain criteria. Now, what is that criteria that we have to meet? Well, for the combined method, so let's do an example here. We want to look at how pH impacts the solubility of magnesium hydroxide. pH and magnesium hydroxide solubility. pH would be, acid. We already can see, pOH is going to impact it here. And so here in equation 1, we'll have the KSP equation, magnesium hydroxide. Solid goes to magnesium ion and 2 hydroxide. And then in equation 2, etc., we look at how H or hydronium impacts this. And so what will hydronium attack in this equilibrium up here? OH minus. And we have 2 OH minuses. So what we're going to do is we're going to take 2 hydroniums plus 2 OH minus. This is going to make what? 2 2 waters. All right, let's just make sure. Actually,
Extra water.
yeah,
Or water.
4 waters. Let's see if that balances. So we have 6 hydrogens here plus 2 hydrogens here is 8 hydrogens. 2 oxygens plus 2 oxygens, 4 oxygens. It's going to be 4 waters. So it's done. All right, the combined method works if the first step is very small. So let's take a look at the KSP here. Would you consider 1.8 times 10 minus 11 pretty small? Yeah. And the second step has to be very large. And do you know what the K for this reaction is? Usually we say that strong acid and strong base, K is very, very, very large. But in this case, we can get the number because look at the reverse. What is the reverse reaction? KW. And so this is 1 over KW. But KW is taking 2 waters. 2 waters, H2O plus H2O makes a hydronium and a hydroxide. But this is double KW. So if it's double KW, do we do 1 over 2 times KW or do we do 1 over KW squared? It's going to be KW squared. And so we meet the criteria for combined. When we use the combined method, equation 1 must be very small, which it is, and equation 2 must be very large, which it is. And then we'll have the combined equation. The combined equation is, we just add these 2 equations up. And so it's going to be magnesium hydroxide, solid, plus 2 hydroniums. Hydroxides cancel. This is going to yield magnesium 2 plus 4 H2O liquid. And then the K for the combined is just equal to the KSP over KW squared. And then we can just go ahead and plug in, our ice. We can say 2 things. One, we could say at initial pH. Well, initial pH gives us our initial hydronium. Or 2, we could say at a pH of, what is a solubility? At a pH of means the hydronium is at equilibrium. Does that, in other words, the pH is going to tell us the hydronium. The pH will tell us the hydronium either initial or equilibrium. Initial or equilibrium, and it depends on how it's worded. So for example, if they say at initial pH of that, well, obviously it's going to be initial. But if they say what is the soluble at this pH, well, that's got to be equilibrium. Otherwise, pH changes. Okay, so let's do a combined method. But it doesn't have to be hydroxide. Hydroxide's a pretty good base. Are there other bases? Yeah, there are other bases out there. And so what are some of the other bases that are out there? Let's take a look. Sulfide is one, but sulfide's special. So I'm going to talk about sulfide in a little bit. Well, we have a lot of other bases here. For example, phosphate is a base, carbonate's a base. Well, we don't have any amides in here. But we could do, for example, we could do carbonate. Let's see. We can see what the solubility is. But carbonate's a little bit more complicated because it's a dibasic base. Something like fluoride might be a lot easier. It's a monobasic base. And so let's take a look at magnesium fluoride, and then we'll go to something like magnesium carbonate.
we just don't have a
So magnesium fluoride should be pH dependent. The reason it should be pH dependent is because not because magnesium ions are neutral, it's because of fluoride ions. These are basic. It's a base. And therefore this has got to be pH dependent because fluoride is a base that can react with acid. So this would be equation 1. Equation 2 is hydronium. Hydronium is going to attack the fluoride. And so we'll have 2 hydroniums plus fluoride, 2 fluorides. Is going to give us 2 HF plus 2 H2O liquid. At the top equation is KSP. So we look at the KSP value. It's 3.7 times 10 minus 8, which is pretty small. And the smaller this is, the better the combined method works. The bottom equation, what is that though? Usually when we have a strong acid react with a weak base, we call that very, very large. Okay, but now we need a number for this. And so take a look at the reverse reaction. If you look at the reverse reaction, what is that? That's Ka, but it's double Ka. So K for this step is just equal to 1 over Ka for HF. And since we doubled it, we'll have to square it. And so now we can do the combined equation. The combined equation is going to be NgF2 solid plus 2 hydroniums. The fluorides cancel, yields magnesium 2 plus HF. So the K for the combined is equal to the KSP divided by the Ka squared for HM. Then we can do an ice table here. So a question for this might be, what is the solubility in pure water? So calculate the solubility in pure water. So based on how this splits, we can set up the ice table. Actually, we'll go ahead and set up the ice table here. The magnesium fluoride solid goes to magnesium 2 plus 2 fluoride. We say initially nothing's dissolved, and so it's 0, 0. And then this is going to be plus S, S being the solubility, this is going to be plus 2S. So this is going to be S and then 2S here in molar. And so then the KSP is going to equal the magnesium concentration, which is S, times the fluoride concentration squared. The fluoride concentration is double the solubility, and we're going to square it. And so this is going to come out to 4S cubed. And then S is just going to equal KSP divided by 4. And then we'll take the cube root of that. And so let's take a look at the KSP value for this. The KSP value for magnesium fluoride is 3.7 times 10 to the minus 8. So it's 3.7 times 10 to the minus 8 divided by 4. And then take the cube root of that. And just raise it to the 1/3 power. 2.0992 times 10 to the minus 3. Okay, so that would be the solubility in pure water. Okay, the next thing is, okay, is this going to be more soluble in acid or base? Look at this. In acid, it's going to shift it to the right. And so I'm going to keep it simpler here. let's calculate the solubility in a buffer this time. And so we're going to calculate the solubility in, let's say, a pH 4 buffer. So the next calculation is calculate the solubility in a pH 4.00 buffer. Well, if the pH is 4.00, then the hydronium ion concentration, the hydrogen ion concentration is just going to equal 1.0 times 10 to the minus 4 molar. It's 2 sig figs. Okay, is that initial or equilibrium? It's, yeah, initial, it's going to be 1.0 times 10 to the minus 4, but it's a buffer. So even if there's a change here, the buffer counters the change so that hopefully at the end it stays the same here. So what is the change? The change in this case is going to be minus 2s. But based on buffer properties, if we lose some of the hydronium, more will be made to compensate because it's a buffer. Buffers try to maintain a stable pH. So we're going to assume the pH didn't change much with the loss of hydronium here because the buffer will counter that. And so the magnesium is 0 because we start off with nothing in there, and the HF is 0. And so this is going to be plus S, this is going to be plus S. And so at equilibrium, this will be S and S. And so here in the combined is going to be the magnesium concentration times the HF concentration.
I think the HF is supposed to have 2.
Yeah, sorry, HF 2, HF. So this would be 2S. This would be 2S. Thanks. And so it'll be times the HF concentration squared divided by the hydronium ion concentration squared. And so the magnesium concentration is S, the HF concentration is 2S quantity squared, and the hydronium ion concentration is 1.0 times 10 to the minus 4 quantity squared here. So we need to calculate the K combined. Here. So the K combined is equal to the KSP, which was 1.8 times 10 to the minus 11, divided by the Ka squared. The Ka for HF, we have to look that up. Here. This page. Six 6.6 times 10 to the minus 4. So I'll get 1.8 times 10 to the minus 11 divided by 6.6 times 10 to the minus 4 squared. Oops. So I'll divide it one more time by 6.6 times 10 to the minus 4. And I get 4.1322 times 10 to the minus 5. Okay, times 1 times 10 to the minus 4 squared. Divided by 4. And then take the cube root of that. 4.6922 times 10 to the minus 5.
Where are you getting that from?
This?
Yeah.
I just do this, so this is K combined is equal to this, so multiply both sides by that. Divide by 4,
Oh.
take the cube root. What was the solubility of water? 10 to the negative 3.
Yeah.
So we would expect it to be more soluble in acid than in pure water. This is our calculation.
You go over here's all the calculations.
Okay, how I got the solubility?
Yeah.
All right, so first we calculate the K combined, and then we're solving for S. S would be the solubility. I don't know. Let me double check the calculation. Yeah, 4.1322 times 10 to the minus 5 is K combined. Uh-huh.
Sorry, who's that? Did you still need him to go over it? Did you still need him to go over it?
Oh, well, I know you have to take combined, but I did it, I'm getting a different S.
Okay, let me check my S value. And so I'm taking this one times this. So multiplying both sides by 10 to the minus 8. And then dividing it by 4. And then taking the cube root of that. What did you get?
Zero one times 10 to the negative 4.
1.01 times 10 to the negative 4. Anybody else? For some reason I've got the same number. We'll check this later. We'll analyze this result later. Check later.
Okay, I got what you got. So when we calculated the S for, just magnesium chloride and S being 2.0992 times 10 to the negative third, that was just like an aside calculation, that was not necessary for this calculation.
That was not necessary for this calculation. For this it's a separate calculation.
Okay.
Yeah. So we didn't really have to calculate the solubility in pure water. But that's just showing the difference in the calculation. So this is one way we can manipulate the pH because one of these ions is pH dependent. That is, it's a base, potentially an acid. And so this is called the KSPA combined method. The reason it's called KSPA is because there's KSP and KA involved. So it's SP and A, KSPA. And so seeing how acid interacts with the KSP equation. Sulfide is a little bit different. So this is KSPA is normal, like we just did. And then we have something else. If we look at sulfides, you see every sulfide has this footnote B. Tin sulfide B, silver sulfide B, iron 2 sulfide B. So what is footnote B? Well, let's take a look at footnote B. For solubility equilibrium of the type MS, solid, plus H2O. Okay. Footnote B refers to this. Whenever I have a sulfide, let's just take a generic sulfide. Sulfides is special. We have to treat sulfides differently. And there's a reason we have to treat them differently. So we have MS solid, where M is just some 2+ metal cation. If we look at the normal KSP equation, we have M2+ plus S2 minus. There's a problem with the normal KSP equation, and that is sulfide is too powerful of a base to exist in water. On this chart, sulfide is misplaced. There. Do you see the green arrow there? Sulfide is not 10 to the minus 12, it's 10 to the minus 19 places it below here, which makes it more powerful than hydroxide. The most powerful base that can exist in water is hydroxide, so sulfide's too powerful of a base to exist in water. And so what happens is the sulfide immediately attacks water. That would be the strongest acid present. And sulfide attacks water, what does it form? Well, water is the acid, sulfide's a base, and it's a proton transfer reaction. It forms hydrogen sulfide ion, HS minus, and hydroxide ion, OH minus. So sulfide plucks the hydrogen off water. Now HS minus is not a strong base, so it's not going to pluck it off completely. But sulfide is a powerful base. And so what we end up with is this, MS solid, the sulfides cancel because sulfide can't exist in water, plus H2O liquid yields M2 plus HS minus plus OH minus. This equation is called KSP dagger, double dagger. And so we differentiate that as being unique. KSP double dagger is like this. We can have KSPA double dagger as well. So this is KSP double dagger, and this is what we do when we have water, but this is going to be sensitive to pH as well because it's HS minus and OH minus. OH minus is strong base, HS minus is weak base, amphoteric. And so let's take a look at KSPA double dagger now. So KSPA double dagger. KSPA double dagger is we just take this equation and see what reacts with acid. And so this is, we'll take the KSP double dagger, that is MS solid plus H2O liquid, goes to M2 plus HS minus plus OH minus. I'm just rewriting it here. So this is our KSP double dagger. And we have to add water to this because to react with the sulfide. Now hydronium, if hydronium is going to attack something, what would it attack first? The HS minus or the OH minus? The OH minus. So hydronium hydroxide, this is going to form 2H2O liquid. K for this equation is, well, look at the reverse. The reverse equation is just Kw. And so K for this is 1 over Kw. But there's another base present, and the other base present is going to be HS minus. So H3O plus HS minus, which is amphoteric, but in this case, with strong acids can act as a base. What does this form?
H2O?
Yeah. This is going to form H2S and water. Okay, look at the reverse reaction and tell me what that is. Yeah, this is Ka. So this is K, 1 over Ka for H2S. So now what we're going to do is combine these. When we combine these, we're going to get MS solid plus the H2Os cancel, hydroxide cancel, the HS minus. That's going to give us 2 hydroniums. This is going to go to M2 plus H2S plus 2 H2Os. This is called KSPA double dagger. Now KSPA double dagger is going to equal the M plus concentration times the H2S concentration divided by the hydronium ion concentration squared. That would be KSPA double dagger. Now KSP double dagger is different. The KSP double dagger, I forgot to write the equation earlier. The KSP double dagger is equal to the M plus 2 plus concentration times the HS minus concentration times the OH minus concentration. That's what it would be. H2O is pure. So we set up an ice table with this, and then we can do ice table style calculations, either with KSP double dagger or KSP8 double dagger. And so sulfides are a bit more trickier, more involved than other species. There are ways we can increase solubility by just taking advantage of Le Chablais' principle. And so, KSPF is one of those. Okay, it's like this, KSPA. It's also combined method. So an example of that would be something like silver chloride. Solid goes to silver ion plus chloride ion. Okay, if we can remove silver ions or we can remove chloride ions, we can increase the solubility. And so if we can decrease and or decrease silver ions or decrease chloride ions, it'll shift the equilibrium to the right. Right shift. Okay. So one of the ways of removing this, like chloride how can we remove chloride? We need something that likes chloride more than silver ions. So can you think of something that likes chloride ions more than silver ions? So we want to set up a competition.
Sodium.
Sodium doesn't. Sodium and chloride will stay apart from one another until you force them together by evaporating all the water. I mean, it will form a sodium chloride lattice. I'm talking about something that will precipitate up with it. And so one of the things we could look at is try to find something like does something else like chloride more, like mercury. If we added mercury 1, if we look at mercury 1 as 1.3 times 10 minus 18, but we need to, in this case, we need to calculate the solubility versus silver. Silver chloride is down here at 1.8 times 10 minus 10. So it looks like mercury, although it splits up differently, this splits up into 3, might like chloride better. We can check the solubility. And so we can put a competing cation. If we put a competing cation, it might precipitate in preference to silver. Does that make sense? Mm-hmm. Another thing is we could try to take advantage of redox and just destroy the chloride. Do you know how we could destroy the chloride? We might try to convert the chloride into chlorine by using a powerful, what? If we use a powerful oxidizer, yeah, we could get rid of the chloride. Although it's hard, you know, because here's chloride. We need something more powerful than chlorine. So what's a more powerful oxidizer than chlorine? We'll take a look at the chart here. I guess we could use gold 3, but would you want to use gold to? No. We could use chlorite in acid. We could use lead 4 oxide, bromate, permanganate. Permanganate's common, it's not so expensive. This is actually very common. We could use potassium permanganate. If we put potassium permanganate and mix it with this, it'll oxidize the chloride to chlorine. And then as we get rid of the chlorine, this will shift to the right. And so permanganate would work. What else would work? You know, manganese 3, hydrogen peroxide. It has to be fairly concentrated. These are 1 molar concentration, so household won't do it. Silver 2 plus is weird. Ozone. So that's one way. Likewise, we can try to get rid of the silver ions. One way we could get rid of the silver ions is use a reducing agent to convert silver ions into silver metal. And so, what would a reducing agent be that could do that? So to convert silver ions into silver metal, we need a reducing agent that's stronger than silver. So what's a reducing agent that's stronger than silver? How about iron 2? Would that do it? Yeah, iron 2 would do it. How about mercury liquid? No, that won't do it. And so anything down here would do it. This is manganese, iodide, do it, etc. And so we can convert silver ion into silver metal. That's one way. But both of those methods will work. But there's a cleaner method, and rather than destroying that, what we can do is we can tie it up. We can tie it up using a Lewis base to make a complex. So for example, cyanide. If we add cyanide in here, what that cyanide's going to do is it's going to attack the silver. It won't attack the chloride. Cyanide will attack the silver to make dicyanoargentate 1. Look at the Kf for this, 10 to the 18. Extremely favorable. And so this should be very effective at removing silver ions. And once they're complex with cyano ligands, it's very hard to break those off. We can use EDTA, ethylene diamine tetraacetato, which will complex with the silver. We could use ethylene diamine. We could use ammonia. In fact, that's what we use in lab. you guys generated silver chloride, and the way we dissolved that silver chloride was by adding ammonia. What the ammonia did is it removed the silver ions. And, here, do we have time?
Pretty much out.
We're out of time. Okay. Let me stop here. Then we'll talk about KFs next time.